So today's deep dive is into a field of science that, let's be honest,
It's a tough one.
it's a really tough one. Our sources say it's known to cause confusion, anxiety, and even actual heartbreak.
Yeah, that's the word they used. But that's okay, because that's our mission today, right? We're here to guide you through all that weirdness.
Exactly. We're going to try and distill the key insights from our sources to understand quantum physics, the science of the very, very small.
Right, the physics of atoms and light. But the key takeaway, and what we really want to explore, is how this theory, which is arguably the most successful scientific theory of the last 100 years, didn't just, stay in the micro world.
No, it fundamentally created the world we all live in today.
It really did.
And that's a point our sources stress over and over. Quantum physics, or QP, it might deal with these tiny particles you can't see, but it absolutely punches far above its weight class.
Oh, completely. This isn't some obscure theoretical outpost that only a few physicists care about. We are undeniably living in a quantum age.
That's such a critical statement. I mean, it's not just philosophy in a lab notebook.
No, not at all. It has completely changed the way we used to live into the way we live now. I mean, think about it. Quantum mechanics, it permeates everything we do.
When we say everything, we really mean everything you interact with. Your computer right now, your phone.
The basic stability of matter, the fact that your desk is solid, is a quantum mechanical effect.
Which is just wild to think about. We rely on it every single second. From the screen you're looking at to the microchip processing our voices. And yet
the core concepts are still so mind-boggling. They just defy our everyday experience. And that brings us right back to that warning our sources give. Quantum reality is, well, it's not intuitive.
not at all. And that brings us to the core quantum shockers that really break our classical intuition. The big one is that at its deepest level, reality is not some, clockwork predictable machine.
No, the universe plays like a game of chance.
A game of chance. And that concept of chance, of probability, is where the confusion really starts, isn't it?
It is, because when we talk about probability in quantum physics, we're not just saying, oh, we don't know enough about the system, so we have to guess. That's not it at all.
Right. This isn't like flipping a coin where, in theory, you could calculate the outcome if you knew everything.
Exactly. The sources are really clear on this. The probabilities are not a measure of what we don't know, our ignorance. They are intrinsic to the quantum theory itself. It's a fundamental property of reality.
So you can't get around them no matter how good your instruments get.
You can't.
Yeah.
And that is a huge departure. It suggests reality itself is fundamentally blurry until we force its hand by looking.
Which leads us to these strange behaviors we're going to explore today. Things like superposition
Where a particle is in multiple states at once.
and entanglement, which Einstein famously called, what was it, spooky action at a distance.
That's the one. But our mission here is to move past that initial confusion, to turn those shocking ideas into functional knowledge, to show you how scientists and engineers have actually used these strange rules to build the future.
Okay, let's unpack that with a really staggering example of how quantum mechanics influences the universe.
I think I know where you're going with this.
We're going to start with a massive paradox. How does the physics of the very, very small, the subatomic world, influence the biggest, most violent, and most mysterious objects in all of space?
Black holes.
Black holes. And the story starts over half a century ago on a very specific date,
Yeah.
December 12th, 1970.
Right. That was the day NASA launched a small Scout B rocket. It took off from an offshore platform just off the coast of Kenya,
And its payload was a satellite named Uhuru.
which is Swahili for freedom, a really fitting name because Uhuru was designed to free us from the limitations of our own atmosphere.
Exactly. Our atmosphere, thankfully, blocks most of the high-energy radiation from space, like X-rays. But that also means we were blind to a whole chunk of the universe.
We were. So the significance of Uhuru was that it was the first space telescope dedicated entirely to observing those X-rays. For the first time, we had a window into the most energetic, violent events in the cosmos.
Superheating gas, stellar explosions, the real cosmic battlegrounds.
And in 1971, the data from Uhuru revealed something truly incredible. Scientists were looking at the constellation Cygnus, the swan.
And they found an object, Cygnus X1, that up until then was pretty much just a mythical mathematical beast.
A black hole, something that, a lot of people thought only existed on paper.
And these things are fearsome. They're formed when gravity gets so immense it literally puts a rip in the fabric of space-time.
And their scale is just, it's hard to even comprehend. We're talking millions, sometimes billions of times the mass of our sun.
The classical view was that they were a one-way trip to oblivion. Once you cross that event horizon, the point of no return, nothing gets out, not even light.
They were seen as these permanent sinks. Anything that fell in was gone forever. But this created a huge theoretical problem, the information paradox. Basically, the laws of physics say information can't be destroyed, so where did it go?
And this is where the quantum world makes its grand, shocking entrance into the macro universe. In 1974, Stephen Hawking used quantum principles to theorize that something did escape.
He said radiation escapes. And it was a shocking claim at the time, but the mechanism, which we now call Hawking radiation, is this beautiful link between the micro and macro worlds.
It all starts with a concept that just shatters our idea of nothingness, right?
Right.
Our intuition says empty space is, well, empty.
And quantum physics says absolutely not. The sources describe it as being seething with possibility. The vacuum is constantly fluctuating with energy.
And those fluctuations create what are called virtual particle pairs.
Exactly. A particle and its antiparticle, like an electron and a positron. They spontaneously appear out of the vacuum. They exist for an impossibly short amount of time. They sort of dance around a bit.
And then they just annihilate each other and disappear back into nothing.
Right. They borrow a tiny bit of energy from the vacuum to exist, and then they pay it back. Now imagine this happening right on the edge of a black hole's event horizon.
The point of no return.
The point of no return. If just by chance one of the particles in that pair falls in, it gets trapped.
So it can't annihilate its partner anymore.
It can't. And that partner particle is now stranded. It's no longer virtual. It's a real particle because the black hole's gravity has essentially paid its energy debt to the vacuum.
So instead of winking out of existence, that partner particle is now free to fly off into space.
Correct. And to a distant observer, like us, it looks like radiation is coming from the black hole. That is Hawking radiation.
And the really stunning revelation here is the implication. If a black hole is emitting radiation, it's losing energy. And since E equals mc squared,
That should be losing mass.
the black hole is actually evaporating. These giant cosmic monsters are slowly, glacially being defeated by the physics of the very small.
It's an incredible intellectual achievement. Now, we should add some context here. For a big black hole, like the one in our own galaxy, this process would take trillions and trillions of years.
Longer than the current age of the universe, by a lot.
By a lot. But the point stands. The mechanism is there. They are not permanent. And it's this amazing connection between the tiniest quantum jitters and the fate of the largest objects in the cosmos.
Okay, so moving from these giant cosmic objects, let's dive into the core foundations of quantum mechanics itself. Because to really understand things like Hawking radiation or the lasers we'll talk about later, we have to go back to how this whole radical idea even started.
Right, and it really arose as a solution to a problem that was deeply confusing physicists about 100 years ago.
The problem of light.
The problem of light, yeah. By the early 20th century, the clear classical line between the physics of particles and the physics of waves had gotten, well, incredibly murky.
Classically, it was simple. You had particles, like tiny billiard balls, discrete solid things, and you had waves, like in the ocean extended, spread out things.
But the evidence for light just didn't fit one or the other. In some experiments, light behaved exactly like a wave. It would show interference patterns, diffraction, all the classic wave behaviors.
But in other experiments, it had to be described as a collection of particles. Einstein's work on the photoelectric effect, for example. It only works if light arrives in these discrete little packets, which we now call photons.
So it was a wave sometimes and a particle at other times, a total contradiction from a classical perspective.
And the quantum solution was to create a new kind of physics quantum mechanics that just accepted this bizarre wave-particle duality as a fundamental property of reality.
Right, and this new theory was really solidified around the time of the famous 1927 Solvay conference in Brussels. You had all the giants there, Bohr, Heisenberg, Schrödinger, Einstein, all gathered to debate and codify this new radical theory.
And it was radical because it completely tossed out the old paradigm that had governed physics for centuries. Specifically, it tossed out classical determinism.
This is probably the most fundamental break. In classical Newtonian physics, you have this idea of a clockwork universe.
The idea that if you knew the exact position and momentum of every single particle in the universe at one moment,
and you knew the laws of physics, you could, in principle, calculate the entire future and the entire past perfectly.
So even something that looks random to us, like rolling dice, is only random because we don't have enough information.
Exactly. The randomness is just a measure of our ignorance. But the underlying process is totally deterministic. Quantum mechanics just throws that entire idea out the window.
It replaces that certainty with a universe that only allows for probabilistic predictions. And this is the part that Einstein just couldn't stand.
Right, leading to his famous line, God does not play dice with the universe.
And Bohr's response was, stop telling God what to do.
But the distinction is so important. In quantum theory, the probability is baked in. It's intrinsic to reality itself.
So even if you have the most complete description possible of a quantum system, you know everything the laws of physics allow you to know, the best you can do is spate probabilities.
That's it. You might say there's a 50% chance this electron's spin is up and a 50% chance it's down. The physics gives you the odds, but it does not and cannot tell you the outcome of any single event.
And this probabilistic nature brings us to maybe the weirdest idea of all, the role of the observer. Or maybe, more accurately, the act of measurement.
Right. In our classical world, looking at the moon doesn't change the moon. External reality is independent of us.
But quantum mechanics makes this strange separation between what a system is doing when we're not looking at it and what we see when we do look at it.
The two descriptions are mathematically completely different. So let's take a single electron. When we're not observing it, we can't say where it is.
So what is it, mathematically?
It's described by a wave function. And this wave function is basically a wave of probabilities spread out over space. The electron is said to be in a state of superposition.
A combination of all the possible outcomes, all at once.
Exactly. It's in a state of pure potential, but the moment we measure it, the moment we interact with it to find its position, that entire wave of possibilities instantly collapses.
And we find the electron in one single specific location. It appears to us as if it had been a solid little particle sitting there all along.
Right. And that collapse is the deep, lingering mystery that physicists have been arguing about for a century.
Because the theory itself doesn't tell us why or how that happens.
It's totally silent on that.
Right.
What happens to all the other possibilities that weren't realized? What is it about the act of measurement that forces reality to choose one outcome over all the others?
That's the measurement problem. We have the math to predict the odds with incredible accuracy, but we don't know the mechanism behind the collapse.
We don't. But despite that deep philosophical weirdness, the predictive power is just uncanny. And that power has had a profound impact on modern life, which leads us right into its applications.
It's the perfect transition. Let's look at how this strange probabilistic physics gives us the most accurate time standards we have. Something we all use every day without even thinking about it.
Atomic clocks.
Atomic clocks.
And the need for them really came from the fact that our old ways of keeping time weren't stable enough. Tracking time by the Earth's rotation. That changes.
Right, plate tectonics, seismic events, even the moon drifting away slowly. It all affects the length of a day by tiny amounts.
So we needed something anchored not to a spinning planet, but to the unchanging laws of physics itself. And that's where the quantum structure of the atom comes in.
The electrons orbiting a nucleus can only exist in very specific, discrete energy levels, like rungs on a ladder.
Right, they can't be in between the rungs. And to jump up to a higher rung, an electron needs to absorb a photon, a packet of light energy.
But not just any photon. It has to be perfectly tuned.
Perfectly tuned. It has to have a very specific, precise frequency to make that jump. And that unique frequency is like a quantum signature for that particular type of atom.
And because that signature never changes, it's based on the fundamental laws of physics, it gives us this incredibly reliable frequency standard. It's like a perfect natural pendulum.
And today, the official international definition of 1 second is based on counting the oscillations of a cesium-133 atom. We're talking about counting over 9 billion cycles, just to define 1 second.
It's 9,192,631,707 Erlius cycles. That specific, unchanging number is what provides the stability that makes so much of modern life possible.
Which leads us directly to something every single person listening probably uses constantly. The Global Positioning System, GPS.
It's amazing how tied we are to atomic clocks through GPS.
The system is so complex, but it feels so simple to us. The US-based GPS system has over 30 satellites orbiting the Earth, and each one has multiple, highly accurate atomic clocks on board.
So when your phone uses GPS, it's listening for signals from at least 4 of those satellites. And that signal contains the satellite's position and, crucially, the exact time the signal was sent.
That timestamp is the absolute key. Your phone measures how long the signal took to arrive. Since we know the speed of light, it's a simple calculation. Distance equals rate times time.
But because that signal travels so incredibly fast, even a tiny, tiny error in the satellite's clock would throw the whole calculation off.
Oh, completely. If the clocks were off by just a millionth of a second, your position would be off by hundreds of meters. And this is where it gets even cooler because we also have to account for Einstein's theories of relativity.
Right. The satellites are moving fast, and they're in weaker gravity than we are on the surface.
So their clocks actually run slightly faster than ours. They have to constantly and automatically correct for both special and general relativity, or the whole GPS system would fail within minutes.
It's this beautiful convergence of quantum mechanics providing the stable clock and relativity providing the necessary corrections to make them all agree.
It is, and we just take it for granted. This incredible atomic clock technology is just baked into our daily lives now.
And the technology is still moving forward. Researchers are pushing for even more precision, which brings us to the next generation, optical atomic clocks.
Right, optical clocks are a huge leap forward. They use lasers, which have a much, much higher frequency than the microwaves used in cesium clocks.
So they need a different atom, like strontium. Let's talk about the work of Jun Yee's group, for example. They use a carefully tuned laser to put an electron in the strontium atom into a quantum superposition.
So it's both in its ground state and its excited state at the same time. He calls it a quantum pendulum.
And this pendulum is swinging at nearly 1 billion cycles per second.
That enormous frequency is the secret to the precision. Think of it like a ruler. If your ruler only has marks every inch, you can only measure so accurately.
But if your ruler has 1 billion marks per inch,
Your measurement becomes incredibly sensitive. These strontium optical clocks are about 100,000 times more precise than the cesium clocks that run GPS.
that is just a staggering leap. And what can you do with that kind of precision? You can measure Einstein's general relativity here on Earth.
Exactly. We know that gravity warps space-time. The stronger the gravity, the slower time runs.
So a person at the top of a tall building where gravity is slightly weaker experiences time passing just a tiny fraction faster than someone at street level.
A difference that was, until recently, completely immeasurable. But these optical clocks are so sensitive, they can detect it.
The sources say that if you raise one of these clocks by just a few hundred microns, the width of a human hair, you can measure a discrepancy in the passage of time.
It's that sensitive. The clock is no longer just a timepiece. It's a sensor for the fundamental structure of space-time itself. It's connecting gravity and quantum mechanics in this really profound way.
And the technology enabling all this precision, both in the clocks and in other areas we'll discuss, is another key quantum invention: the laser.
Right. And to understand what makes a laser so special, it helps to contrast it with, say, an old-fashioned light bulb.
A light bulb is just chaos. You heat up a filament, the atoms vibrate randomly, and they spit out photons in all directions at all sorts of different wavelengths.
The analogy in our sources is perfect. It's like a mob of people all singing at a different pitch.
Whereas a laser is pure order. It's like a choir of 1,000,000,000,000,000 people, all with perfect pitch, all singing the exact same note at the exact same time.
And that coherence, that purity, comes from a quantum process called stimulated emission.
So how does that work?
It starts with an electron that's been energized or pumped up into a high-energy state. Now, it could just fall back down on its own and emit a random photon. That's spontaneous emission, like in a light bulb.
But in stimulated emission, something triggers it.
Exactly. A photon with just the right frequency happens to pass by that excited atom. It doesn't get absorbed. Instead, it stimulates the electron to drop down to its lower energy state, and in doing so, it emits a second photon.
And the quantum magic is that this second photon is an exact clone of the first one.
A perfect replica. Same frequency, same phase, same direction of travel. It's quantum mechanical amplification. One photon becomes two identical twins.
And if you put these excited atoms between two mirrors, those photons bounce back and forth, creating an avalanche of identical photons.
And when some of that light escapes through one of the mirrors, which is only partially reflective, you get that intense, pure, coherent beam we call a laser.
This laser gives us the ultimate ruler. Since the speed of light is constant, we can use these high-frequency light waves to measure tiny changes in distance with incredible precision.
Which brings us to one of the greatest scientific achievements of the 21st century, the Laser Interferometer Gravitational Wave Observatory, or LIGO.
Einstein predicted that massive accelerating objects, like two black holes colliding, would create ripples in space-time itself, gravitational waves.
Though he thought they'd be far too small to ever detect.
But a century later, we built LIGO to do just that.
Yeah.
The design is, in principle, simple, but the engineering is just monumental.
They built two identical facilities miles apart. At each one, they split a powerful, stable laser beam and send it down two long arms, 2.5 miles each, at right angles.
And when the two beams return and recombine, they're set up to perfectly cancel each other out. So normally the detector sees nothing.
But if a gravitational wave passes through, it will stretch one arm and squeeze the other by an infinitesimal amount. We're talking a distance 1/10,000th the diameter of a proton.
An unbelievably small change. But it's enough to knock the laser beams slightly out of sync.
So they no longer cancel out perfectly. A little bit of light leaks out and hits the detector, and that tiny flicker of light is the signal. It's direct proof that space-time itself has rippled.
And in 2015, that incredible gamble paid off.
It really did. They detected the collision of two black holes. The energy released in that final moment was more than all the stars in the observable universe combined, all released as gravitational waves.
A complete revolution in astronomy. And it was only possible because of the quantum laser giving us a ruler sensitive enough to measure the quivering of space-time itself.
That's just
Yeah.
a profound achievement.
That power brings us to the final frontier we'll discuss today, where we find that concept Einstein hated so much, spooky action at a distance.
Quantum entanglement.
Entanglement.
It's definitely the most counterintuitive and maybe the most powerful aspect of quantum mechanics. It forces us to just abandon our classical idea that an object can only be influenced by its immediate surroundings.
The sources use a great analogy. Imagine a machine that spits out pairs of coins. You flip one, it's 50-50 heads or tails. Totally random. But whenever you flip both coins from a pair, they always match. Head-head or tail-tail. Every single time.
Now, you might think they were just pre-programmed, but in the quantum version, the outcome isn't decided until you measure it. So you could take one coin to the moon, flip them both at the exact same instant.
And the moment you see heads on Earth, instantly that the one on the moon is also heads, no signal could have traveled between them.
And that's exactly how entangled particles behave. They share one single quantum state, no matter how far apart they are. Measuring one instantly determines the state of the other.
And this isn't just a thought experiment anymore. Experiments have proven this is a real feature of our universe.
Undeniably real. And now we're learning how to put this spooky action to work in cryptography, secure communications, and most famously, quantum computing.
Which all starts with a qubit, the quantum version of a classical bit.
Right, all of modern computing boils down to bits, zeros or ones, on or off. A qubit is different. It can exist in a superposition of both the zero state and the one state simultaneously.
So instead of just being at the north or south pole of a sphere, like a classical bit, a qubit can be anywhere on the surface of that sphere.
It opens up this vast new space for computation. But the real power comes when you entangle multiple qubits together.
Because then the number of states they can explore grows exponentially. The sources say that to describe just a few hundred entangled qubits, you'd need more classical bits than there are atoms in the known universe.
That's the extravagance of the quantum language. It allows the computer to explore this immense computational landscape all at once.
And it's a huge industry now. Google, IBM, Microsoft, they're all in this race to build a powerful, stable quantum computer.
Which brings us to the huge engineering challenge you see in all the pictures. The cooling. That giant gold-colored chandelier, that's not the computer.
No, that's the refrigerator. The computer is a tiny chip at the very bottom.
And that whole setup is designed to cool that chip to just a fraction of a degree above absolute zero. Colder than deep space.
Why does it have to be so insanely cold?
Because superposition and entanglement are incredibly fragile. Any stray heat, vibration, or magnetic field, any noise at all, can destroy the quantum state and ruin the calculation. The cold removes that noise.
Once it's stable, they manipulate the qubits with precise microwave pulses, and then at the very end, they measure the result, which forces the qubits to collapse into a classical 0 or 1.
But there's a problem. These systems are inherently error-prone. The qubits can just spontaneously decay out of their quantum state.
So the current generation of quantum computers can't correct their own errors yet.
Not fully. The raw data has to be sent to a classical supercomputer for heavy-duty error correction and post-processing. They work together.
Which brings us to the future. Quantum computers aren't going to replace your laptop. You won't be running quantum PowerPoint.
No, they're specialized tools. They'll be good at simulating other quantum systems, for designing new drugs or materials, and for solving incredibly complex optimization problems.
And the experts predict that within the next 5 to 10 years, we'll see a clear demonstration of a quantum computer solving a problem that is just completely impossible for any classical computer.
The future is integrated. You'll have classical, AI, and quantum processors all working together, each playing to its strengths.
What a journey. We've gone from microscopic particles dictating time to their influence on evaporating black holes, detecting gravitational waves, and fueling the next generation of computing.
The bottom line is, after a century of theory, we're finally gaining real engineering control over the quantum realm. These strange features are now built into how you navigate the world every single day.
And yet, even with all this progress, the deep philosophical mysteries are still there. We know the rules of the game with incredible precision, but we still don't fully understand why the rules are what they are.
We don't, but we know that we need to understand that fundamental level of interaction to do these big things, like building clocks that can measure the warping of time over the width of a human hair.
It makes you think. In 50 years, people will be talking about technologies that are normal to them, but seem like pure science fiction to us today.
Entanglement and superposition might just be commonplace ideas. And that leaves us with a final thought for you to consider.
Quantum mechanics has shown us very clearly that we cannot always trust our intuition. Our common sense is built on our everyday classical world, and it fails spectacularly at the quantum level.
We have to rely on our mathematical understanding, not our gut feeling, to make progress. Which makes you wonder, what other fundamental aspects of reality might we be failing to grasp today, simply because they defy that ingrained classical intuition?